Hello everyone, welcome back to Caltex Academy. In case you're new, my name is Julius and thank you for joining this great family of academic stars. If you're not one of academic star, what are you waiting for? Go ahead and subscribe to the channel and you definitely become one of the academic stars. So today on our board, we have gas laws. And this topic cut across physics and chemistry. So if you are a physics star or if you are a chemistry star, then you are taken care of by just only one video. So on our topic, specific topic of today, we're looking at Boyle's law. We know there are three gas laws, so we shall look at them one by one. In our next video, we shall look at Charles' law. If this sounds great, come closer and let's dive into the video. So our question 1 says, state Boyle's law and write its mathematical expression. Now from here, anything to do with mathematical expression always followed in by some calculation. Now we need to state this law and we derive its mathematical expression, and we shall use that mathematical expression to solve part B of this question, which says a volume of 375 cubic centimeter has a pressure of 20 atmosphere. What will be its volume if pressure is reduced to 15 atmosphere? I think that question sounds interesting, and it is only if we state our law correctly. So without further ado, let us state our law. So Boyle's law states that the volume of a fixed mass of gas is inversely proportional to its pressure at a constant temperature. We must make sure that the temperature is kept constant. Then now its volume will be inversely proportional to the pressure. Or we can also say the pressure is inversely proportional to the volume. All are considered to be correct. Let's write our answer down here, and we start with part A of the question. Yeah, so since we already know our law, we can go ahead and write its mathematical expression. From what we have just given here, we said Boyle's law states that the volume of a fixed mass of a gas is inversely proportional to its pressure at constant temperature. Now from here, we can see that the volume V is inversely proportional, so we have this symbol, to its pressure. So from here, we need to remove this proportionality sign. Whenever we remove proportionality sign, we always put in constant of that proportionality. So we have V is equals to K over P, where K is the proportionality constant. So from here, we can write this expression in terms of K by multiplying both sides of this expression with P. Now we can repeat writing it and multiply this side here by P, also the left hand side with P, and we simply cross our P from the right hand side, and definitely this becomes PV, and let me bring K to the left hand side, and we have K equals to PV. Now since K is a constant, meaning we can vary these volumes. Like, let me have some illustration here. According to this law, if we have pressure and volume altered in a way of having something maybe similar to that, and we give our pressure here up, if this is pressure P, and we write this P continuously, you can see that our P is getting smaller and smaller and smaller. Now when we put there V beginning from here, our V is beginning small and is growing bigger and bigger and bigger. And that is the meaning of inverse proportion. As one quantity reduces, the other quantity must increase. And if we plot a graph of these two quantities, like if this is our volume V and this is pressure, and the graph will just simply be something like that. That is what inverse proportional graphs look like. So from here, as I've just mentioned, as the volume increases, the pressure reduces, or as the pressure reduces, the volume must increase. So let's put that statement down and we continue with our final conclusion of the formula here. So from here, we realize that from the statement I've just made, we have pressure 1 times volume 1. This must give us pressure 2 times volume 2. It will continue as many times as you want. Pressure 3, volume 3. And in most cases in calculation, we just compare two parts. So we can write this. In fact, this is the same as our constant K. So let's write any two, maybe 1 and 2. Should be the neighbors. We cannot write pressure 1, volume 1, and then pressure 3, volume 3, leaving out these two. It should always be the neighbors, this and that, or 2, 2, and 3, 3. So from here, I'll take the initial one here, and we have when the pressure is 1, volume 1, and we equate it to pressure 2, also volume 2, this becomes one of the formula we can use for our calculation of question related to volume and pressure. Now, from here, let us collect data of our question B and we calculate it. So this is the data from our part B of the questions that asks us to calculate the volume if the pressure changes from P1 with 20 atmosphere and to P2 of 15 atmosphere when the initial volume is 375 cubic centimeters. Now we can calculate our volume in cubic meter. It doesn't matter, meaning we have to change our number here into meter cube. But if you wish to have them all in the same unit, we can go ahead and also work out this question in centimeter cube. So from Boyle's law, now in this law, we're talking about the mathematical expression pressure 1 times volume 1 when it changes to pressure 2 times volume 2. This must be constant. So from here, our main interest is getting V2, the subject. So we can also go ahead and insert your numbers directly to this form of the equation and work out. Or you can make what is missing to be the subject. I think let us make what is missing to be the subject by now. We divide both sides by pressure 2 such that we get our V2 alone. Now let me rewrite this again, and we have V1, P1, P2, and V2. And this time we're dividing both sides by P2. So the pressure 2 here will cancel, and let's rewrite it in terms of V2, and our V2 will be equivalent to this side, that is P1 and V1 over P2. Now at the same time, you find some people making the calculation together with the units, I think that is somehow tiresome, but in this question, let's work with the unit and see how we can end up getting the same unit that is required as volume. And in our next example, we shall work for only questions without the units involved and just simply insert our unit at the end of our working. And to remind you, we'll have 4 numbers to work in this example or in this Boyle's law video. So let's move on and insert what is necessary here, starting with our pressure 1 being 20 atmosphere. So V2 is given by pressure 1, that is 20. As I mentioned earlier on, we need to indicate the units here at the moment, atmosphere, and we are multiplying this by volume 1, and our volume 1 is 375 in cubic centimeter. And we're dividing this by the pressure 2, and pressure 2 is 15 atmosphere. So from here, you notice that since we are multiplying, we can move on and cancel these units that are the same. Then we can enter into a calculator and do some calculation. Let me first work the numerator alone and see what it will bring for us. Here we have 20 times 375. That brings for me, okay, let me put it down as the volume, to an numerator as 7,500 over the denominator 15. And remember, our unit is still here, cubic centimeter. So if we divide this answer of ours with 15, we get 500. So our unit is cubic centimeter. And this becomes our answer for question number 1. So let's proceed to question number 2 immediately here. In question number 2, that says a given mass of gas occupies a volume of 200 cubic centimeter at a pressure of 5 atmosphere. At what pressure will the gas have a volume of 800 cubic centimeter? So this time we're calculating for pressure. In our question 1, we calculated for volume. Now let's again collect data from here, and we say from the question here, the first parameter that appears was the volume, and we have V equals to 200 cubic centimeter. And the pressure is pressure 1. I think we need to also give some subscript here, as V1 and P1 is 5 atmosphere. So in short form, we just write the first 3 letters to represent atmosphere. So at what pressure? So meaning the second pressure, P2, is missing, and we can give there a question mark. Will the gas have a volume of 800 cubic centimeter? So this is volume 2, that is represented by 800 cubic centimeter. So from here, we can quote our formula that says pressure 1 times volume 1 must give us pressure 2 times volume 2. And it's not always compulsory that you have to make the missing parameter to be the subject. You can go ahead and substitute directly. And in our working, I would think we're going to do that but we are not going to consider the units because we know the volume for this specific question is measured in cubic centimeter. So after calculation, we know that our unit is also going to be in cubic centimeter. So let's move on and insert what is there. Pressure 1 is 5 atmosphere, and you're multiplying this by volume 1, and our volume 1 is 200. So this must give us pressure 2 is what is missing, and right there P2 times again volume 2, and our volume 2 happens to be 800, so we can put it here 800. So if we multiply 5 times 200, we get 1000. This gives us always letter comes after a number, so P2 times 800, so we have 800 P2. Now we can rearrange having this 800 on this side such that our unknown will just be from the left hand side here. So our 1000 comes here. Now this time we're dividing both sides here by 800 in order for us to obtain only P. So the 800 will have to cancel, and these two zeros will also cancel with that. Now our pressure 2 will just be 10 over 8, or we can reduce it down as pressure 2 to be, of course, by, if we divide 10 to 8, it goes 1, and the balance is 2 over 8. And we know that this one also can reduce by 2, 1, by 2, 4. So simply our pressure 2 would be 1 whole number and 1/4, and that is atmosphere. So this becomes our solution for question number 2. So from here, let us move to question number 3 and see how it looks like. In question 3, it says, a certain mass of gas occupies 250 cubic centimeter at 25 degrees Celsius and 750 millimeter of mercury. Calculate its volume at 25 degrees Celsius if pressure changes to 760 millimeter mercury in SI units. Now, what does this question refers us to do? Here, from the definition or from Boyle's law, we said at a constant temperature. So that constant temperature is not specified always. Now, at room temperature, we had here 25 degrees Celsius, 25 degrees Celsius. Room temperatures depend on which location you are in. Now, you consider the temperature is the same, reflecting that it is constant. So, again, the next thing here is pressure can be expressed in different terms. We saw in atmosphere as one of the unit. Here is millimeter mercury. It can be in Newton per square meter, or it can be in pascals. So for this specific question, our pressure has been given in millimeter of mercury. So, and the question is demanding us to also calculate our new pressure in SI unit. So the SI unit of pressure, we know it is pascals or Newton per square meter. Okay, so let's collect our data for this question. Now, the first thing we have to do here is to check on our first value. Let's say a certain mass of gas occupies 250 cubic centimeters. So this becomes our volume number 1. So our V1 is given by 250 cubic centimeter. Now the temperature, we don't need to write it somewhere because it's just constant. It's not reflected in our formula, so we just have to leave it out. And 750 millimeter of mercury becomes our pressure number 1, and we can also record it down here. 750 millimeters of mercury. Now calculate its volume at the same temperature here. If the pressure changes to that, meaning our volume 2 is missing. So we can represent with our question mark, and pressure 2 has now gone into the standard pressure here, 760 millimeter of mercury. So again, we can quote our formula that says pressure 1 times volume 1 should give us pressure 2 times volume 2. So we can move on and make our substitution. Pressure 1 is 750. As I mentioned earlier on, we're not going to insert our unit, so just give our unit at the end of our working. And we know that since our V1 is in cubic centimeter, then our V2 will also be in cubic centimeter. But remember, we have to convert into SI unit as the question has demanded us to do so. So we multiply this by our V1, which is 250. This should give us pressure 2, which is 760 millimeter of mercury, times the missing volume, that is V2. Now we can multiply the left hand side, and we had 750 multiplying 250, that brings 1,000. 187,500 from the left hand side, and the right hand side, we just join this together, 760 V2. Now let's again rearrange. We just swap it around, and we have 760 V2 is equivalent to our 187,500. So at this stage here, we're dividing all these sides here with the coefficient of V2, and that is 760. Also here, 760. Then our 760 will cancel from the left hand side, and we're left with only V2. This should be equivalent to, so if we divide our answer here with the denominator, and that is 760, we will get, and round this to 2 decimal places, so our V2, and when you're rounding, we always include this sign here, that is approximation sign, and we have 0.71 cubic centimeter. Now, since we need to convert this into cubic meter, then we can go ahead and multiply this by 1 million. But where is that 1 million coming from? So I have to show for you how that 1 million comes about by just remembering one thing. We say 1 meter contains 100 centimeter. Now, if we cube because our unit here is cube, meaning we need to cube all these two sides here. What do we get? Okay, this is cube, also here is cubed. So we can distribute 3 to m and to 1, and cube of 1 is just 1. So m cube will also be here. So here, when you cube 100, it's like multiplying 100 times 100 times 100, and the two zeros will be doubled up and becomes 3 zeros, and we have here 1 million. Also, centimeter, if you cube it, we get cubic centimeter. So here we have 1 million. Some people make this separation of this place value with dot. Is allowed in other countries. So for me, I'm using comma. Any of your choice you can take, either using dot or comma. Now we have that. And now our answer is 246.71 cubic centimeter, meaning we can place it somewhere here, and we have 246.71 cubic centimeter. What would be the equivalent of this? So we say that is x, then we can cross multiply. Now we'll start with the one with x. So x times 1 million, we will get 1 million x. So we have here 1 million x. Now this is equivalent to 1 times this value will remain the same, 246.71, and we are going to leave these units out because the unit is just going to be this one here for our value for x. So we can divide these sides. Let's divide both sides by 1 million. And since this one came from this multiplication, I think it's a good idea to first rewrite it again and have our step there intact. So we have 1 million x. So it will be equivalent to the same value, 246.71. Now at this stage, we can move on and have our division sign inserted here. So we have our 1 million getting removed from the left hand side and it's getting transferred to our right hand side here. So we can cancel our 1 million. Now, when we divide our answer by 1 million, we simply get the value for x as 2.4671 exponent -4, and that becomes cubic meter. Therefore, our volume 2 is that value, and we can reduce this to 2 decimal places. So we have 2.47 exponent -4 cubic meter. So this is our answer for the third question. If you have some question, please go ahead and tag it in the comment section. I'll get back to you to answer wherever necessary. So let's move to our last question of this video down here. So in our last question number 4, it says, at a constant temperature, a gas of 540 millimeter mercury pressure occupies a volume of 300 liters. The gas is made to expand and occupy a volume of 600 liters. What is the new gas pressure in SI units? So from here, we're also given our pressure in millimeter mercury. Our volume this time is in liters, and we're asked to calculate the pressure in SI unit. So our SI unit is either Newton per square centimeter or pascals. And we have to collect our data to start working this question out. So from here, at a constant temperature, a gas at 540 millimeter mercury. So this becomes our pressure number 1, and that is 540 millimeter of mercury. Occupies a volume of 300 liters. So V1 becomes 300 liters. Now, the next one here is volume 2, and that is 600. This gas expanded twice. It doubled. Now, what do you think will the pressure to be like if the volume doubled? Is the question's demand here, and we need to give our answer also in SI unit of pascals. So let's move on and tackle this number. Now again, we can quote our formula from Boyle's law. P1 V1 equals P2 V2. Now our pressure 1 is 540, and we are multiplying it by volume 1, that is 300, and we equate it to pressure 2, and that is what is not known. Then we are multiplying it by volume 2, and our volume 2 is 600. So let's go ahead and multiply these numbers and see that if we enter this into a calculator, and you have 540 multiplies by 300, we'll get 162,000. And of course, if you multiply this number with the letter, it will just be connecting these two things together, the letter and the number. And again, I always like my unknown to be in the left-hand side. So 600 P2, maybe let me use a different color here. This will give us our 162,000. So let's go ahead and divide both sides by 600. Now we can see that this 600 from the left hand side will just cancel, and we can keep reducing this. So our pressure 2 should give us, so we can divide this and have 270. So what could be the unit? According to our unit of the first one here, we have millimeter mercury. So our unit here also will be millimeter mercury. So the next thing here, or the next question for us is, how do you convert millimeter mercury into pascals? So this question is easy to answer. Now, we need to come up with a standard atmospheric pressure that is measured in 760 millimeter of mercury, giving us 101,325 pascals. So how about if you have 270 millimeter of mercury? How would this be in our SI unit here? So we can give it there letter Y, and we cross multiply. So we can start by multiplying with where the unknown is. So 760 times Y, we get 760. As we always leave out our units, knowing that to trace the unit is easier, you come to where your unknown is and you move upward to see your unit. So here, the next cell is multiplying this answer of ours, that is 270 by 101,325. So let's do that multiplication. 270 times 101,325. So we get this figure. Let's get more space, and we have our 700 still, and 60 times Y from this side here. So we have the results of 27,357,750. So we can divide both sides of our expression here by 760 to get our value of Y. Yeah, so again, this cancels and we get our Y as, so when we divide our result here by the denominator 760, we will get 35,997.03947. And of course, this one is in pascals. So if you wish, you can write it in standard form or scientific notation, or you can just round it off to 2 decimal places. I think this time let us write it in scientific notation. So our pressure 2 therefore becomes, in scientific notation, we have to move this dot to the last digit here. So 1, 2, 3, 4. Now we can place our dot here, and this one rounds to 6. So 60 times 10 exponent 4, because we have moved there 4 steps, 1, 2, 3, and 4. And that becomes our answer in SI unit of pascals or Newton per square meter. So thank you for watching up to this time. See you in the next video where we shall look at Charles' law. See you in that video. Peace out.